Hello all, I welcome you all to this video lecture. So the topic of the video lecture is game playing. Before we let into the topic, I want to share some basic information about game playing in artificial intelligence. Game playing is a popular application of artificial intelligence. It involves development of computer program to play games such as chess, playing cards, then crossword puzzles in online, etc. So the world first AI-based game when the human was Deep Blue. It is a chess game developed by IBM. It is a chess game developed by IBM that defeated the world chess champion Gary Kasparov in 1997. After this, many number of AI-based games are developed. So in this slide one, we are going to know some basic types of games. So normally game is referred as an adversarial search problem. Why it is called as adversarial in the sense, if we consider the playing environment as a multi-agent environment or a two-player environment, here two players are acting in an environment with the aim of win the game. So they are here the agents are provided equal chances for each other. So here, but the actions taken by them are opponent towards one another. So only it is referred as a adversarial search problem. So in AI, the most common games are fully observable and competitive environment. So competitive in the sense, the agent is work with the motto to win the game and defeat the opponent. So in this presentation, we are going to see about the following topic. First one is formal definition of game. Then what is meant by game tree? How to obtain a optimal decision by viewing this game tree? What is meant by min-max algorithm and certain properties of a min-max algorithm. So this is the formal definition of game. So for any problem, the problem solving methodology will be described by using the four major components. The first one is the initial state, then the successor function, then goal test, and then finally path cast. Likewise, here the game problem is also solved by certain number of basic components. So here in addition, we are need to concentrate certain extra elements such as players and actions. So like the fundamental components, here also we are started with the initial state. So the initial state specifies how the game environment is startup. So the players represent how many number of players and who starts the first. That informations are represented in the players. So action represents the set of legal moves for each possible player. So if a particular player is in the current state and by performing certain action, he will reach some other state that is represented as the result of S, A. It is also represented as a transition model. Okay. So next one is terminal test. Terminal test is nothing but a goal test. In normal problem definition, we generally refer it as the goal test, whether that particular agent reached the goal or not. Like this, here we check whether that particular player reached the terminal state or not. So if the person is reached the terminal state, then the game get end. Then the game will stop there. Next one is about the utility functions. So utility function is also called as an objective function or a payoff function. So it is mainly applied to the terminal nodes. So the node which is in the terminal nodes need to find the utility value. Based on the utility value only, we can able to select the optimal decision. So for example, consider a game chess. Here the outcome is win For a player, the outcome may be he may win the game or lose the game or draw. So if the person win the game in the sense, he will get plus 1 points. If he lost, he get minus 1 point. If the game gets draw, then he gets half points. So zero sum game. It is one of the important type of game playing method. So zero sum game, the total payoff of all the player is always same. For example, here chess, if a person lost in the sense his point is zero and the opponent person win means his point is one. So when we calculate the total payoff, its value is equal to one. Likewise, if the first player is win, the value become 1. If the 1 for first player and the value becomes 0 for the second player. Here also when we calculate the total payoff, its value is equal to 1. Even if the match gets draws, both the players will get half of point and the total payoff value will be equal to 1. So here at any stage the resultant value is 1. So this type of gaming problem is referred as a zero sum game. So next we are going to see about the game tree. So, in order to solve any type of problem, the first step we need to do is uh, find out the search space and need to generate the search tree or search graph. It is based on the convenience of the problem. So here for gaming problems, the game tree is very useful to find the optimal decision. So it is defined by the initial state. So here it is the initial state with the set of actions. That set of actions will lead the successor states. So here we are move towards here we are expanding the nodes of the tree until we are reaching the terminal node. Once we reach the terminal node, we will find out the utility value for the terminal node. So this is an example tree for the game tic-tac-toe. So here initially always the initial chances provide towards the max player, then the alternative chances provide towards the win player. Okay. So finally when the player reaches the terminal node, the utility value for that terminal node is calculated. So next is about the optimal decisions in game. So, in order to take the optimal decision, the first step we need to generate is the search tree. As that is we saw in the previous slide. We saw in the previous slide. So here we are selecting the optimal solution with the help of this search tree. In adversarial search, the optimal solution is somewhat contingent. So here the in max specifies here initially the max starts its move in the initial state. After that, the min will continue. Then after min, again max will continue. So like this, the game gets continued until any one of the person reaches the goal state. Here is an important term which is referred as one move deep. If a particular game ends after one move, each performed by max and min, then it is called one move deep. It is also called as ply. Ply in the sense, so in general we refer this term as a cycle. So half is performed by one player and another half is performed by another player, and that one complete cycle is referred as a ply. If we got the solution in the single cycle, then it is called one move deep. Okay. So many mix value, min max value. So min max value is nothing but it is the utility value of the terminal node. So after we calculating the utility value of the terminal node, we need to we need to update the value of the intermediate nodes, and then we need to update the value of the root node. Okay. So this is the function. So first we check whether that particular state or node in that particular state is the terminal. So for that, we perform the terminal test. If it is the terminal node, then we calculate the utility value for that terminal node. So otherwise, if that node is the intermediate node, so we need to check whether this is the chance for the max player or whether there is the chance for the min player. If it is the chance for the max player, then the intermediate node's value gets updated based on the successor values. So if it is a max player, then it will select the maximum value of its successor node. If it is the chance for the min player, then the player will select the minimum value of from its successor node. Like this, the intermediate value also gets updated. Node's value also get updated. So consider this tree. It will provide a clear-cut idea about the concept of min-max tree. So this is a two-play game. So one step is taken by the max player, and then one step is taken by the min player, and then finally reach the terminal nodes. So here the upward triangle represents the max player, and the downward triangle represents the min player. So after the player reaches the terminal node, the utility value for each terminal node is calculated and updated. So here now we backtrack towards sorry. Now we backtrack towards the previous node. Here there is a node B. Yeah, in this stage B, C, D are under the control of the minimum player. Here there are two player. One player is referred as the max player, and another player is referred as the min player. So the max player, yeah, always the games get started with the max player. So in the initial stage, the move was started by the max player. After that, the move gets continued by the min player with the aim that both are trying to optimally take a decision. So in B, the min player is in the need to take the decision. So here it is the min player, so he always need try to select the minimum value from its successor. So he select the action B1, and first he select the action B1 and find the utility value of this node. Its value is 3, and then he select the next successor node and find the better utility value of this node. Its value is 12. So it keeps on 3 for 3, and then check the another node too. It execute the action B3 and checks the utility value of this node. Its value is 8. When comparing these three only minimum value, so B gets updated with 3. Like that, here from C, the min player select the action which leads to the minimum value. Here C1 is the action that leads to the minimum value. So C gets updated with its with the value 2. Likewise, D select the action which provides the minimum value. So D selects the action D3, and its value gets updated with the minimum value of its terminal node 2. So here all the nodes in this level gets updated. So it's all the intermediate level nodes value utility values get updated. Next, it is the chance for the max player. The here max player is in the root node. So max player always prefer the successor with the maximum value. So it checks. So by executing the action A1, it finds the value of this node B. Its value is 3. After that, it checks execute the action A2 and checks the value of C. Its value is 2. After that, it executes the value of action 3 and checks the value of D, and its value is also 2. When comparing these three, B gets the maximum utility value. So the A gets the value of A is updated with the value of B. So 3 gets updated to the root node. So this is the general min-max algorithm. So what we have seen in the previous slides is detailedly explained here. So min-max algorithm is a recursive or backtracking algorithm, which is mainly used in decision making and game theory. It provides optimal move for both the players. So min-max algorithm uses recursion to search through the game tree. So here it performs depth first search. So once we expand the node, and if we reach the terminal node, then we backtrack and expand the another possible way to reach the some other terminal node and select best by comparing all the terminal nodes. So Minimax algorithm performs the depth first search for exploration of the game tree. So the Minimax algorithm proceeds all the way down to the terminal node of the tree and then backtrack to the root node to find the value for the root node. Here the two players are referred as max known. First player is referred as the max player and the second player is referred as the min player. So from the initial state, the first move is provided to the max player. Max player always choose the maximum value from its successor and min player always choose a minimum value from its successor. So this is another working example of a min-max algorithm. So here the pink rounded circle is represented as the max player and the blue rounded circle is represented as the min player. Initially, the value for max is assigned as minus infinity and the value for the minimum player is assigned as plus infinity. So the value for maximum player is assigned as minus infinity and minimum player is assigned as plus infinity. As I always say that in the initial state, it is the chance for maximizer to start. To start, here the search tree is generated completely and the utility value of the terminal nodes are also calculated. So now we are working in a backward directions to find the values for the utility values for this intermediate node and also utility value for this initial node. So So for node D, we are going to calculate the utility value. For this, we first find its successor. There are two successor H and I. So first it compares the value of H with its the utility normal utility value. So initially we are assigning the max value as minus infinity. So it compared it with the H value. So minus one comma from minus one comma minus infinity, it is a maximizer, isn't it? So in this level, we mainly concentrate on the maximum value of the successor. So when comparing these two minus one and minus infinity, the maximum value is minus one. So it is updated towards the node D. So then it check whether there is any other child or not. Yes, there is a child that is I. So we need to expand it to and find the utility value of I. So now currently D is updated with minus one. After that, it expands the node I. Here the value of I is 4. Now it compare these two value and then select the maximum value. When comparing the minus 1 and 4, 4 is the maximum value. So 4 gets updated with the D. Likewise, here E, first we compare the value of J with the minimum max value. So J's value is 2 and max value is minus infinity. From that, the maximum value is 2. It is updated towards C. And that it check the another possible child. Yes, there is a child K. Its value is 6. Then it checks the value of 2 and 6. From this, the maximum value is 6. So 6 get updated towards E. Likewise, F and G are updated with its maximum child value. So for F, the maximum child value is minus 3. And for G, the maximum child value is 7. Now again we backtrack towards previous level. So here B and C are the nodes. Here the chances provided towards the min player. Min player always prefer the successor with the minimum value. So here B there are two successor. One is D and another one is E. So here the minimum value is only for D and that value gets updated towards B. So B gets updated with the 4. Likewise C gets updated with the value minimum successor value. So here the C gets updated with the value minus 3. So the next step, we are going to update the value of the root node. So in the initial state, the chance is always provided to the maximizer. So here A is under the max player. So here he needed to select the node value which have maximum value among its successor. So here B is selected because comparing B and C, B has the maximum utility value and that utility value is updated towards A. So here the optimal decision to win the game by max player is A to B, B to D and then D to I. So A to B, B to D and then D to I. So next is about the properties of min-max algorithm. For any algorithm, the performance measuring elements are these three. They are whether that particular algorithm is complete or not, optimal or not, what is the time complexity for that algorithm, and then finally what is the space complexity for the algorithm. Here, the min-max algorithm is complete. It will definitely find the solution for the problem once the solution is exists in the search tree. And it is also optimal because here both the opponents are play the game with the mindset to select the optimal move. So time complexity. Here we are performing the depth first search. So here we are using the concept of depth first search. So time complexity is also similar towards the depth first search. The time complexity of this algorithm is order of B power m. Here B represents the branching factor and m represents the maximum depth of the tree. And the space complexity of the min-max algorithm is similar to DFS and it is order of Bm. Next is about the algorithm for min-max search. So this is the general algorithm for the min-max search. So here we are providing the input state, the problem's input state as argument for the min-max decision function, and then finally we are in need to return the actions as the result. So here there are two players. One is max player and another one is min player. So max player always used to select the max value from its successor and min player always used to select the min value from its successor. So max player needed to return the utility value as well as min player is also used to return the utility value for that particular node. So before that, we need to check whether that state is terminal state or not. So if it is terminal state, we need to calculate the utility value of the state. So for max player, the initial value is assigned as minus infinity. For min player, the initial value is assigned as plus infinity. So from the current state, there are n number of actions are available. The max player always select the maximum value and update the V value and then finally return the utility value. Here V represents the utility value. Likewise, there are n number of actions are also available to the min player. The min player always select the minimum value by comparing this and then he will update the utility value and then finally returns the utility value. These are certain limitation of the min-max algorithm. The main drawback of the min-max algorithm is it's really so for complex problem such as chess, checkerboard, Go, etc. Because here in the min-max algorithm, the number of nodes to expand is exponential to the number of state space available. So this type of game has a huge branching factor and the player has lot of choice to decide. So this limitation of min-max algorithms can be improved further by using the concept of alpha beta pruning in game playing. Thank you.